Okay, now the final thing in this unit is reaction mechanisms. And reaction mechanisms are actually pretty easy if you are, one, willing to follow rules, and two, willing to think outside of the box. So I'm going to walk you through a little bit, and I'm going to show you an example. And then in the last podcast where I do all the example problems, I'll walk you through an entire problem that goes from determining rate law all the way through analyzing reaction mechanisms. So, what a reaction mechanism is, it's a series of chemical reactions that must occur to determine the rate law for the overall process. So remember when we talked about Hess's law, we talked about how all of a sudden chemical reactions no longer had to occur in one step. Well, now these mechanisms are chemical reactions that have to occur in order to get the overall process. The best example I can use is baking. If you've ever baked before, sometimes you have to do things to parts of the cake or whatever it is before you can start. For example, if you are making a cake from scratch, what you have to do is you have to mix all of your dry ingredients first. You mix all your wet ingredients in a separate bowl, and then you combine them together, because some of the dry ingredients are actually activated by the presence of milk or eggs or water, etc. So you want to make sure you do them separately from each other. When you do them all together, all of a sudden the thing starts to rise, it starts to react beforehand. So a baking of a cake is a good example of a reaction mechanism. So you mix your dry ingredients in one bowl, you mix your wet ingredients in another bowl, you combine them together, and you get your cake as your final result. Now let's look at it from a chemical perspective. Here's an example. It says the following mechanism has been proposed for the reaction of NO with H2 to form N2O and H2O. So step one that must occur is two molecules of NO must react, and when they react, for some reason they form N2O2. That N2O2 is then used to form H2, and N2O2 reacts with the H2 to form N2O and H2O. So the overall reaction was 2NO gas plus H2 gas to form N2O gas plus H2O. Some of these reactions we'll be looking at, they can't occur normally. Like, I can't get NO to react with H2 to form N2O and H2O. So it must occur in this stepwise process. So this N2O must be formed first, but this N2O2 must be formed first, but this N2O2 is actually what's called an intermediate, because it's a compound, sometimes very unstable even, that is produced in one reaction and consumed in another, but it's never found in the overall. It's literally used as a middleman to get from the start to the finish. So otherwise, what would have to happen in this chemical reaction is I'd have to have two molecules of NO collide with one molecule of H2 at the exact same moment in order to form N2O and H2O. And the probability of that occurring is very, 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 very small. Even if you started with moles upon moles upon moles, billions and trillions and quadrillions of molecules in a mixture, the chance of all of that occurring where two molecules of NO will hit at the exact same moment is very slim. But if the NOs bump into each other, which is very likely, and combine to form N2O2, I have a greater chance of this reaction occurring. So let's look at a slightly different example, and I want to talk about how the reaction order is related to the rate law. So here's a different example. The reaction 2NO plus Cl2 yields 2NoCl obeys the rate law. Rate is equal to K times NO to the second times Cl2 to the first. The following mechanism has been proposed. The question here is this a appropriate mechanism? So I'll write this. Is this a possible mechanism? Okay, that's basically the question I'm trying to answer in this problem. Now, there are only two rules that govern mechanisms. Rule number one is the sum of the individual reactions equals the overall reaction. Okay? So if I add up these two things, does it equal what they gave me right here? Okay? So let's add these up real fast. So I cross out anything that's on both sides of the reaction. So my NoCl2, my intermediate, is on both sides, so those cancel, and I get 2NO, because I have an NO plus an NO, plus a Cl2 yields 2NOCl. Does that equal the overall? Yes, it does. Okay, so rule number 1 has been followed. Now let's look at rule number 2. Rule number 2 is the rate law for the slow step equals the overall rate law. Okay, now, how do I determine what's my slow step? What's called a slow step, and it literally does mean slow, is that's a step that has to occur before anything else can occur. Now, that doesn't mean it has to be reaction number 1. What I really mean is, and I just said that in a confusing manner, what I mean is the slow step takes the longest amount of time. So if I said to you this whole process takes 1 hour, then my slow step might take 55 minutes of that 60 total minutes. Okay? So that rate law has to be finished. I'm sorry, that reaction step has to finish, and then everything else goes really, really fast. And literally, it's written as slow or fast. Those are the only 2 designations for this reaction. So let me determine the rate laws for each of these reactions and see if one of them matches the overall. And if one of them matches the overall, that means that one is my slow step. Okay, so how do I write a rate law? Well, I told you now, the only way to write a rate law is with experimental data. But in the absence of experimental data, and you may want to make a note of this on the side, in the absence of experimental data, use the coefficients in the balanced chemical reaction. So, my rate law in this reaction, because I have no experimental to work from, is I've got a 1 coefficient in front of the NO and a 1 in front of the Cl2. So my NO is to the first. My Cl2 will also be to the first. Okay? Does this match this one up here? No. No, it doesn't. So this is not the slow step. Okay? That is not the that step cannot be my slow step. Now I look at my other reaction. And I look at that other reaction and I say, okay, I'm going to erase a couple of things here just so I have a little bit more room. Okay, I look at this second reaction. I see rate is equal to K times the concentration of NoCl2 times the concentration of NO. But I have a problem, okay? And you're looking at this and you go, why? Why? He just did it right. No, I did it right, but there's a problem. And the problem is the NoCl2. The problem is NoCl2 is an intermediate. And since intermediates don't appear in the overall reaction, they cannot appear in a rate law. Write that down. Intermediates never in rate law. Okay? My intermediate can never be in the rate law. So I have to take it out. But I can't just leave it blank. I have to fill in what created my NoCl2. Well, my NoCl2 was created from an NO and from a Cl2. Well, wait a second. Now I have two NOs. Well, NO times NO is NO to the second. Now, does this match my overall? Yes, it does, which means that this is my slow step. Okay? So, is this a possible mechanism? Well, let me see. The rate law for the slow step equals the overall rate law. Well, my reaction 2 happens to equal my overall rate law, so that's possible. And when I added them up, they added up to be equal to the overall. Therefore, this is a possible mechanism. Okay? The slow step does not have to be the first step. It does not have to be the last step. It can be any number of different, any one of the steps. Let's do some more examples. Okay, now this one is a little bit of the think outside the box kind of situation. It says, for the hypothetical reaction above, I'm sorry, this is supposed to be 2 and a 2, subscript 2's. For the hypothetical reaction above, give a rate law that shows that the reaction is first order in the reactant XY. Okay, so again, remember that reactants are the only things that can be in rate law. So it says, give a rate law for the reaction that is, I'm sorry, so that it's first order with XY. Well, that's simple. Rate equals K times the concentration of XY, 1 to the first. That's first order. Done. Simple. Give the units for the specific rate constant for this rate law. Okay. Well, remember what I told you. K will always be in the form of 1 over molarity times time. Now, since I am not given an actual seconds, hours, etc. here, I would just write time. But if you want to insert seconds, that's fine. Or hours, minutes, doesn't matter. Now, my units on M is always 1 less than the overall reaction order. My overall reaction order is a 1. So it's 1 minus 1, which is 0. Well, anything to the 0 is 1. So my actual units here are just 1 over time. I know, it's kind of funky. You'll see it as we do more examples, and it'll make more sense. And it says, propose a mechanism that is consistent with both the rate law and the stoichiometry, which means that when I propose my mechanism, it has to add up to equal the overall reaction, and the rate law for my slow step has to equal my overall rate law. Now, there's a lot of different there's no right or wrong answer to this, as long as it follows those two rules that I just gave you. So I'm going to propose a very simple mechanism, and I'm going to show you why this one works, and I'm going to do a second one and show you why it doesn't work. So here's a simple mechanism. X, Y yields X plus Y. XY plus X plus Y yields X2 plus Y2. Okay, so I'm going to show you 2. Let's do this. Let's change this into let's do this into X, Y yields. Oh, actually, I'm going to show it to you like this. Okay, now you're looking at this going, wait a second, Siegel, you wrote the same thing twice. And I did, except I wrote my slow step in 2 different spots. Okay? In the first one, my slow step is my first reaction, and the second one, my slow step is my second reaction. Now, why does one work and the other one doesn't? Remember, 2 rules. Rule number 1 is it must add up to equal the overall. Well, when I cross out, let me change my color real fast. When I cross out my intermediates, I get 2xy yields x2 plus y2. Same principle over here. Cross out my intermediates, which are these simple xy's. So that rule applies to both of them. So that works. But the rate law for the slow step must equal the overall rate law. So my rate law is k xy to the first. Well, in this one, my rate law will be rate equals k times the concentration of xy. And since the coefficient is a 1, it's to the first. In this one, I have rate equals k times xy, but then I've got an x and a y. And the x and the y are both created from xy. So since I'd be substituting xy in for both x and y, I actually get xy to the third. Here, I think that might have been a little confusing, so let me show you again. I'd have xy times x times y. Okay? This x was created from xy, and this y was also created from xy. And since they're intermediates, they can't be in the rate law. So I have to substitute out what makes them. Well, xy times xy times xy is xy cubed. Okay? So in reality, you can actually write the same reaction mechanism, but because you identify the wrong step as being the slow step, it makes the reaction mechanism not possible. Okay? So this one, again, it adds up, but the reaction mechanism doesn't work, so that is not a possible mechanism. This is. Is there one right answer? No. Because they leave it open-ended, I can write basically anything I want as long as it follows the 2 rules. It adds up to equal the overall, and the rate law for the slow step equals the overall rate law. And that's it. And that's how you do reaction mechanisms. Like I said, in the example problems I'm going to do in the next podcast, everything, I'm going to walk you through every single part of the process, and you can see it from start to finish.